All right, so we are doing the muscular system today, the one everybody, kind of, wants to talk about. And so we're going to go through a little bit of the cellular parts of it. We're not so much going to get into, and we'll get a little bit into like muscles as movers, like whether they're agonists or antagonists. We won't do too much into like flexion, extension, or like the planes of motion, because we're going to get into those tomorrow or next Monday. But today, I will say, like, the muscular system is really exciting. I will say sometimes this is one of the most technical. There's a lot of like little tiny moving parts that they want you to know here. So don't let this PowerPoint intimidate you. Like I said, it is going to come back plenty of times. You're going to get super familiar with all these working parts. But sometimes like these working parts can get a little nerve-wracking just because it sounds like a lot of information. So this is where we're really easing you in, Noel. We're really like we're really hitting you hard on day 3 here. We do that on purpose. I was talking about this the other day, but it's like that's what the PFT program is like. It's like people sign up and we're like, welcome to the PFT program. Here's a bunch of biology. I promise. It gets more digestible and more fun coming up after this. So, all right. So the purpose of today's lesson, that was a great clap, by the way. My ears are ringing. The purpose of today's lesson is to finish up talking about the kinetic chain, right? We talked about the nervous system. That's our control system. We talked about the skeletal system. That's our framework. Now we are talking about the muscular system, which is the workhorse that does all the actual moving, right? So the nervous system is going to tell your muscular system how it's supposed to move, and your muscular system is going to do the moving. So what your muscular system is it is a series of muscles that move your skeleton, right? And technically, and this is just a note for those of you who have been through our PFT 118 anatomy and physiology class. Remember how we talked about how like the levels of organization, right? You got cells that make up tissues, tissues make up organs, organs make up, systems, right? This is where like by that classification, technically every one of these muscles is its very own organ. And so that's where you start to get really deep into the philosophy of muscular. And it's like, well, how many muscles are in the body? And depending on who you ask, there's 500, 300, like it's all over the place here, The same thing is true of the skeletal system. Depending on who you ask, it's around 208, I think is the most acceptable answer. Muscles, it's all over the place because so many people are like, like me, for instance, I think like the adductor magnus, anterior fibers, and the posterior fibers, those are 2 separate muscles. They share an origin, but like they do opposite things. And you don't have muscles that do opposite things. You have muscles that do one thing, so then you have an opposite muscle that does the other thing. So to me, that means it should be classified as 2 separate. So depending on who you ask, you're going to see that. So that is unimportant to the conversation. So really, we just want to understand what our muscles' job is, right? Their job is to generate internal tension in order to manipulate the bones and produce human movement. So our muscular system's job is to be really good at contracting and relaxing, right? And so when I say your muscles need to be good at contracting, what I mean is your muscles need to work with your nervous system in order to move the proteins inside of the cells and overlap those proteins so that a muscle goes from being this long, right, where it might be arranged kind of like this, and then it will slide across itself. Those proteins will actually slide across each other, and that muscle will go from being this long to being this long. And then it can relax back to its normal length. Now, as we move throughout this entire lesson, I'm just going to say one thing here up top that I want you to keep in mind throughout the whole lesson today, and that is this. Muscles can only pull. That's the only thing they can do. Your muscles can shorten and they can relax. They cannot push in the opposite direction. And that sounds kind of surprising when you think about it. You're like, really? Like, there's an exercise called the push-up, but that doesn't mean that that your muscles are pushing. Muscles can pull and they can relax, right? And so when you look at like a muscle pulling, right, it like during a push-up, for instance, right? So I've got a muscle, my pectoralis major, it's going to run, it attaches, it originates like on my breastbone here, and then it runs across and it inserts onto my humerus right over here, right? So when I contract this muscle, what it does is it draws my humerus, it draws this bone to the front of my body like that. So if you look at a push-up, right, and I'll do like a, kind of a, kind of like what you see like when kids do push-ups and they're like super far out to the side here. But just, we'll do this version here. So when I do a push-up, right, you can see I'm moving that bone forward like this. I happen to also be extending my elbow at the same time, which is my tricep doing work. And that's how we know that a push-up works your pectoralis major and your triceps. My triceps are doing elbow extension, and my pectoralis major is doing what's called horizontal adduction. And so when those two things happen simultaneously, I go into this pushing position, but that's because this muscle is pulling and this muscle back here is pulling, right? And so muscles can only pull. We want to keep that in mind throughout this whole lesson. They can pull, but then they can relax back to full length. So they can slide their proteins, and that's the pulling sensation, and then they can relax those proteins back to full length. So if we know that muscles can only pull, right, and we know that that is true, then how the heck do we ever get back into our other position? Like, I would be stuck like this the first time I ever did a push-up, and I would just like walk around like this for the rest of my life. So luckily, the muscle that was contracting can now relax back to full length, and that will allow my arm to return. But I also have opposite muscles on the other side of a joint. So remember, the job of your muscular system is to manipulate the skeletal system, right? And so the way that your muscles are always going to be arranged, they're always going to be arranged where there is one muscle pulling in one direction and another muscle pulling in the opposite direction. So I apologize. I'm gonna go with paint here because I don't know how I'm gonna find the picture that I want. But if you think of like a bone here, right? Here's like a kind of, I only know how to draw dog bones. So there's a bone, right? And you're going to have one muscle that's attaching here. And you're going to have another muscle that attaches on the other side here. And so when those muscles contract, you're either going to go this way or you're going to go that way. And so that's sort of how all of your muscles are arranged. This is the opposite. This one here is the opposite of that one there. And so that's what we're seeing. This muscle can pull and it can relax, and this muscle can pull and it can relax. And that's how we get our skeletal system back to neutral. Do you want to say that work of art? Their job, like I said, is to generate internal tension in order to manipulate our bones and produce human movement. Now, your muscular system is under the control of your nervous system, whether that is, voluntarily being controlled or involuntarily controlled. It doesn't matter. It's still under the control of the nervous system. So, sometimes you're going to have involuntary parts of your nervous system firing your muscles for you. That's what like a stretch reflex is called, right? So if anybody in here has ever, jumped, which I'm sure everybody has, you are experiencing a little bit of a stretch reflex. And so when you rapidly stretch a muscle out, your nervous system gets a big signal from that Golgi tendon organ and from that muscle spindle that says, whoa, we just stretched at the speed of light. We just stretched really fast. We have to contract, otherwise we're going to tear. If we keep stretching at this rate, we're going to get to a place where finally, we overstretch and then we're going to tear off the bone. So in order to protect you, it sends a signal to the nervous system that creates what's called a stretch reflex. And it's a reflex because it's going in the opposite direction, right? So if I rapidly stretch my bicep, what's actually going to happen is my bicep's going to try to contract in the opposite direction. If I rapidly stretch my tricep, then my tricep's going to, I'm sorry, if I totally did the wrong direction. If I rapidly stretch my tricep, it will fire and want to take me in the opposite direction. So what's great about that is we can use it to our advantage. We can use stretch reflexes to our advantage. If I want to jump really high, rather than going down kind of slow, and then jumping, right? Going down slow doesn't trigger that stretch reflex. But if I rapidly drop into the bottom of a squat super fast, my nervous system goes, ugh, we should contract all the leg muscles to keep them from tearing. And that's great because now I want to contract my leg muscles so that I can jump higher. So when I go down really fast, and that'll actually create a small contraction unconsciously, and then I will contract while I'm getting this kind of bonus nervous system contraction, and that'll cause me to jump even higher. And that's what a stretch reflex is. So that's one of the fun things we're going to be looking at, and how it sort of interacts with our nervous system, right? I consciously, somatically decided to do something, but there is also a little bit of autonomic something that's happening there as well. So we will be looking at that later on. And that's basically a lot of the stuff we're going to be talking about today. So one thing about your muscular system is that it is made up of a whole bunch of muscle fibers, and those muscle fibers are kind of a special term that we use to describe like muscular cells. You know, you get the neuron, right? Well, you also have the muscle fiber, right? The neurons make up your nervous system, osteons make up your skeletal system, muscle fibers make up the muscular system. And so when we look at that, right, your muscle is a compilation of all kinds of individual muscle fibers neatly wrapped together to form bundles. And so when I say that, here's what I'm talking about. So muscular layer bundles. So here is, oh my God, that's perfect. Oh, it's gonna have a black background. No. All right, it works. Actually, that actually is still easy to see. Although, no, I can do better. Hold on. You guys know how picky I am about these free Google images. There we go, that'll work. All right, so here is sort of how your muscles are actually arranged. They are bundles of bundles of bundles, right? So here's an individual muscle fiber. This is one muscle cell right here, right? And then what's gonna happen is this muscle cell is gonna be wrapped together with this one and that 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 one. All of those muscle fibers are all gonna be wrapped together, and there's a little like wrapper around the outside of them that's called a fascicle, right? And so this bundle here is a fascicle of muscle fibers. So the wrapper actually isn't necessarily the fascicle. The fascicle is the bundle. The wrapper is a type of fascia. There's a weird distinction. But there you can see like muscle fiber, muscle fiber, muscle fiber, muscle fiber, muscle fiber, right? All those individual ones, and they're all wrapped together in what is called a fascicle. And then you can see here, this big fascicle is made up, you know, there's a fascicle here and another one here and another one here, here, right? All of those fascicles are wrapped together in another layer of fascia that's called your paramecium. And then that whole thing is going to be wrapped in one final layer of fascia that kind of just covers everything to make sure that like none of the fibers get out of order. And that's going to be called your epimecium. So it's a layer of a layer of a layer. I would get somewhat familiar with these layers, but I wouldn't spend like all your time trying to memorize them. But like definitely understanding their arrangement is important, even if you don't necessarily have all the names super well memorized. Yeah, what's up, Irene?
Yeah, you know, can you go back to the picture real quick? It looked like the paramecium and fascicles. Paramecium is on top there, and then fascicle.
Fascicle?
They look the same.
Yeah. So a fascicle. So you see how there's a wrapper around the fascicle?
Yeah.
So the fascicle is all the fibers when they're bundled up, but that wrapper around the outside is like a bit of what's called just fascia. And so fascia is holding it together in what is called a fascicle, right?
Okay.
Just like, I don't know, like you would call a paper bag, but you would call a bag of groceries a bag of groceries, you know?
Got it.
That's, I don't know if that one's a good one. But there we go, right? Like, you've got one fiber. When a whole bunch of muscle fibers are bound together, you call it a fascicle. And you're right, like the paramecium, right? The layer that's surrounding it it is surrounding the whole thing. So the paramecium is actually surrounding this whole thing right here. A paramecium wraps a bunch of fascicles together, right? So the fascia wrapping a bunch of individual muscle fibers together to form a fascicle is all wrapped together with other fascicles to form your paramecium. Does that make sense?
Okay.
You know, it might help. I hate to go back to Microsoft Paint because it's so difficult, but at least I can do different colors.
It's like holding a bunch of straws and having saran wrapped around them.
Yeah, there you go. Right? So we'd have an individual muscle fiber here, right?
Okay.
And then that would be wrapped together with like a bunch of other muscle fibers. I don't know why I'm being so specific about this. Right, and then that whole thing, and then I'm going to wrap this in a different color. So that whole thing is going to be wrapped together in a fascicle. Right? And then a bunch of fascicles are going to be wrapped together.
Got it.
Arg.
Man, that's pretty good.
So there's a bunch of fascicles. Now, again, there would be individual fibers in each of those.
Right.
I'm definitely not going to redraw those. And then that whole thing would be wrapped in your paramecium.
Okay, cool. Thank you.
That would wrap the whole thing together. Now there is one. I right-clicked again. It's so difficult to draw circles, and I had it and I ruined it. So there's your paramecium, right? Now there is another layer just outside the paramecium, which is the epimecium, and those two look really similar, your paramecium and your epimecium. But the difference is the epimecium is not technically a full like part of the muscle. It's really just fascia around the outside. And so that blue section there, that's your paramecium. So this is the paramecium, and it's called right. And so when you look at that, right, you've got oh, I'm sorry, I think I just screwed up. I did screw up. I always do that. God dang it. That's the epimecium. This one is the epimecium. I gotta remember my root words, which stands for epicenter, which I then started writing epicenter. Epimecium. This green one is the paramecium because it's around the perimeter.
And the thickness in between the two is very, very fine.
Yeah, it is. And when you look at fascia, right? So there we go, right? Muscle fiber, fascicle, bunch of fascicles come together, surrounded by a paramecium. Paramecium is surrounded by your epimecium. When I say epimecium, it looks like this: muscle fascia. Hopefully they show us a real. Yeah, I mean, you can kind of see like all the fascial lines throughout the body, right? Look at how all of your muscles kind of wrapped in this white connective tissue. You've seen fascia, by the way. If you've ever like cut meat and you've seen like the silver skin, that kind of white, clearish, stretchy material, that's fascia.
Yeah.
You're actually looking at that epimecium there. And there, I'm sorry to pull up a master, but there you can see that's kind of what it looks like. And then you can kind of see, there's an even better one up top. Yeah, you can kind of see it there. It's like wrapping around the outside there. And so that's actually a lot of times what often gets tight, you know? So for instance, like one of the reasons I think I'm having such a hard time getting my sacrum back in place is because there's what's called your thoracolumbar fascia, which is down here at the bottom of your low back. And like, in order to protect this area, there's actually a lot of fascia here to keep any of the muscles from like moving in a direction they're not supposed to do. And so like when that tightens up, especially if it, yeah, look at that. Good job, internet. It'll start to pull in this kind of X fashion. And that's why sometimes you'll get uneven hips, is because the fascia will pull this way and it'll pull that way. And fascia is like, oh, there you go. Look at that. That's perfect. Look at all that, how thick the fascia is in the low back. And then like, look at it, how thick it is around your rotator cuff too, right? But that's kind of fun. And so when you look at this like deep fascia here, it sometimes makes it really difficult to get your muscles to go back in the direction they're supposed to go. It can really tighten up and kind of hold your body in these different positions. And so that's what a lot of like, that's why a lot of like more, practice has been put in these like percussion massagers, these like massage guns that have gotten so popular in the last few years, is because they like vibrate at such an intense frequency, they kind of beat up that fascia. And at first, when you do that, your fascia like tightens up in response. It's like, ah, and it like fights out and like tightens up like crazy, which is exactly the opposite of what you want it to do. But what we found is if you hold it for longer durations, so about like 2 minutes, it starts to beat the fascia up so much that your nervous system can't keep contracting it, and then it all just relaxes. It's almost like autogenic inhibition, but for fascia. And so it causes like a full relaxation, then you can really start to get into the muscles there. And that's why here's a question for you guys. Noel, Robert, Irene, have any of you guys ever foam rolled your IT band? Have you ever foam rolled all the way down, like down your leg, like here on the side of your thigh?
You talking about like a twist ankle?
So it's, here, I'll show you. So foam rolling your IT band is, so remember I talked about the TFL yesterday, right? Your TFL is this from here to here, and then it becomes your IT band as it travels down to here. So have you ever rolled, like placed a roller on like the side of your thigh, like right here? Has anybody ever done that?
No.
No.
Well,
does it get tight?
It does. Oh, oftentimes, yeah, it does. But here's the thing. It's mostly fascia. Like, that's why it's not even really kind of called a muscle. It's called a band. But here, I'll show you. It's called, your IT band is your iliotibial band. We'll learn that later when we get to knee day or hip day. But here it is. And look, they draw it in white. They don't even draw it like a muscle because it is mostly fascia. You can see it's this big band here. And what'll happen is you'll get runner's knee or runner's hip is what it's called, where you'll get a rubbing sensation on the outside of the knee, or you'll get a rubbing sensation up here at the hip, where basically this muscle will tighten up so much that it starts rubbing on the bone here, or it starts rubbing on the bone down here. So what people will do is they'll foam roll their IT band. But here's why I bring this up. That's what people will often do, but we are finding evidence that says like, stop foam rolling your IT band because it's mostly fascia. It ends up being very painful compared to other foam rolling. And it really just does not feel super awesome. So then it ends up like creating more tightness and inflammation. Like you'll get temporary relief because there's just a lot of heat and a lot of blood flow going to the area. So it'll feel like you made it better. But then that fascia will tighten up over the next couple hours really intensely. And you'll end up like in a situation, making your situation worse. So that's kind of what fascia is, right? Or plantar fasciitis is a similar situation, right? Let's look at your plantar fascia. So your plantar fascia is the webbing on the bottom. Actually, that's great. Look at that picture. The webbing on the bottom of your foot. And sometimes it'll rub, it's supposed to attach right here, but it's also supposed to continue. It attaches here and then continues around to become your Achilles tendon. And so it'll sometimes rub as it's going around the heel here, and you'll get inflammation because of the fact that this is a low blood flow tissue, and not because it's not like muscle. It's similar to muscle, but it's different. And so it'll get really, really inflamed, and you'll get people who will describe this like stabbing sensation in their heel. They'll feel their heels really painful. It's really bad in the morning, after they've been resting for 8 hours, and it has relaxed, and then all of a sudden they start walking around again, and it gets really inflamed and really bad.
I felt that before.
Plantar fasciitis, yeah, it's brutal. The fact that it's good that you got it to go away. A lot of people deal with it for years and years and years and years.
Gone, final.
I love it. So let's go ahead and just really quickly. Sorry, go ahead.
So is it bad to foam roll fascia or just the IT band?
It is kind of bad to foam roll fascia. It kind of depends. I will say this. It kind of depends on how that fascia responds. Like one of the treatments for plantar fasciitis, for instance, is, you can't foam roll at the bottom of your foot because the foam roller is too large, but you can take a golf ball and roll your foot around it. And a lot of people will get like relief from that. And luckily you're walking around on your feet, so your feet stay warm pretty much all day. So it doesn't really have an opportunity to re-tighten up that easily. But yeah, it's interesting. Like we're finding more and more that we really shouldn't use foam rollers on fascia. And that's becoming more of a popular thing. And that's where these percussion massagers are getting so freaking popular, is because they're like, we were right in the middle of kind of coming to this conclusion that we shouldn't, there's a fly in my coffee. We were just getting to this conclusion that we really should not, gross. That we really should not foam roll fascia, and then percussion massage. Percussion massagers came along. I grossed myself out. Percussion. God. Just freaking talk. I didn't find a fly. I found something much worse. Ugh. Okay. Regaining my composure, forgetting that happened, and moving on with my life. Answering your question, we are finding that some muscles respond well to foam rolling your fascia, but not all of it. Because we were in the middle of like kind of coming to this conclusion. It's like, hey, we should stop foam rolling fascia. Because like I was taught to foam roll it, and then we started like doing long-term research, and we were like, hey, like this isn't working. Maybe we shouldn't do this. And then eventually we got to a place where we're like, well, now percussion massagers are here, and they haven't been shown to have that retightening effect that foam rolling did. And so it's interesting. I don't really know 100% how to answer your question. Like, do we say don't foam roll the IT band, don't work on fascia? Or do we say like, well, you could do percussion massages on fascia as long as you hold it for long enough. But what if you held your foam rolling for long enough? What if you just gave it more time? Wouldn't that have the same effect? So it's interesting, Robert. I was taught to foam roll the IT band, and it used to even be in your NASM textbooks as well. Used to find like examples. Now what we're finding instead is that the IT band is just so easily aggravated that what you should do is you should foam roll the TFL. So you should foam roll up here at the TFL and not get into the IT band portion. And as long as you can do that, you're going to kind of be getting the benefit there. Does that make sense? Actually, it probably does. Sense is the wrong question.
yeah, I get it. It's good to give it some SMR, but just not no foam roll.
Yeah, I'd probably like leave it alone. If you get a massage on your IT band, that might be effective. Because they can work on it for longer durations. So anyway, that was a fun little like sidetrack. Let's really quickly go back to how our muscles are arranged. So, like I said, they are bundles of bundles of bundles. Now I started from the small. Actually, I do want to put one more. We got to get the endomysium here. Endomysium, right? The endomysium is that innermost layer, and then you would have like what we would call you know, the individual muscle fiber, that's your muscle cell. And we'll just write that here. We'll say it's a cell. And then a bundle of muscle fibers, different color here. That would be a fascicle. Which fascicle is the important term, to be honest. That's a bundle. Okay, there we go. So I went from small to large. I went with like endo first, then a bunch of endos come together to make up the epi. I'm sorry, to make up the peri, and then a bunch of, you know, the whole thing is wrapped in an epi, right? Let's go in the opposite direction. Let's look at the outermost layer, right? The outermost layer of your muscle is going to be the fascia, right? It's a connective tissue that binds your muscles together in order to keep it moving the way it's intended. You want to have your fascia because, number one, you want to make sure that your muscle doesn't get a chance to like move outside of a bone or get to the wrong side of something. You know, like these are an individual like bunch of fibers. Like when you look at like a relaxed fascicle, right? You got to remember, it's a whole bunch of individual little fibers. It's like a bunch of rubber bands. And when those rubber bands are in a relaxed state, you know, they'll get like a funky shape to them, right? Like, take a look. There's a strained state where they're all straightened out nice and long, but a relaxed state might result in them kind of getting this wavy shape, right? And what we don't want to have happen is we don't want them, when they get into that wavy shape, to somehow suddenly, you know, twist around each other and get into like an odd arrangement, because then next time you pull that muscle, right, they're going to slide across each other in a way that maybe they're really not supposed to slide across each other, right? And that's not something we're looking for, right? We really don't want them to get like tangled up in each other. So you have all these different layers of fascia that are keeping the muscle fibers from tangling up with each other. And so the outermost layer is the fascia, right? The next layer you've got is that epimysium. That's around the outermost layer of the muscle itself. And so the epimysium is going to surround your overall muscle, right? And so it's there kind of surrounding everything. Then your next layer is going to be that perimysium that wraps around the fascicle. And then your final layer is that endomysium wrapping around your cell wall, right? So all of that is going to come together, right? All of that's going to come together in the end to make up your what is called your muscle belly. And then at the very end of your muscle belly, you're going to have a tendon, right? And so the tendon is what's going to actually insert onto a bone, okay? So tendon is the connective tissue that attaches muscles to your bones. They provide, like they're providing a means by which like you interact your muscular system with your skeletal system. So they're like an anchor that pulls on the bones, and then they're attached to the muscle, which is like shortening. So like they're there holding on, and then the muscle gets shortened, so they pull with it. So here's the thing. This is that love-hate relationship that I talked about yesterday with this picture. I love this picture and I hate this picture because like they are showing you ligaments and tendons and they look super similar. So tendons, right? Take a look here. This muscle gets into, it slowly starts to become like this kind of whitish color here. This section is the tendon. This section is the muscle, right? So the muscle comes down. And the other thing I hate about this picture, this kind of makes it look like it's attached to the top of the patella here. And then it makes it look like there's just a tendon that attaches your patella to your tibia. That's not really how it works. The way it actually works, and I always got to like find this one specific picture, but yeah. There it is. Okay, this is actually what it looks like. Do you see how like this picture is kind of drawn in such a way, the tendon runs over top of the whole thing and inserts onto your tibia down here. So it's not stopping here and then picking up down here, it runs over top of it. And that's why, and this is kind of a fun, weird fact, if you do this right now and you touch your kneecap, you can even feel a little bit of weird soft tissue, right? That's because you are touching the tendon as it's running over the kneecap. You can feel you are poking the tendon, you know, right here. You're pinching it between your finger and the bone. Now, this section right in here, right, is technically called like your patellar ligament, and this section up here is called your quadriceps tendon, but it's really all part of the same thing, because otherwise this muscle wouldn't be able to pull on this bone down here, right? We need your quadriceps to be able to pull on your tibia. That's what allows you, you know, by pulling on your quadricep like this, that's what allows you to straighten your leg, right? I pull up like this, right? And that creates that extension motion. Tendons, right? Again, kind of summarizing them, they are connective tissue that attach muscle to bone and provide an anchor for which your muscles can produce force. Now, tendons are similar to ligaments in the sense that like they have limited blood flow as well. So because of that, they also repair very slowly compared to like your muscles. So ligaments attach bone to bone, tendons attach muscles to bones. They both share a very similar characteristic, which is that they both repair very, very slowly. So let's go ahead and look at muscle fight. Actually, questions, comments, concerns. How you guys feeling?
Brad, can tendons and ligaments ever intertwine with each other, or they're two complete separate things?
Yep, they're two totally different things. Yep.
Okay. Yeah,
they look really similar. Yeah.
Okay.
But that doesn't mean they're at all actually similar.
But they can be like right on top of each other.
What's that?
But they can be like on top of each other, like if you have a ligament.
Sure. I mean, you could see them really nearby. Yeah.
Okay.
Yeah. A lot of times the ligaments will be deep and the muscles will be, the tendons will be superficial.
That's where they test your reflexes, right?
Yeah, the quadriceps tendon. Yeah, that's how they test the reflexes. Here, I'll show you. I'm so bad at hitting it. I always tend to miss it. Whenever I try to,
that's what the doctors do.
Whenever I try to do this, I always miss the spot. But yeah, what they're doing when they do that is they are smacking your quadriceps tendon right here. And so here's the thing. Remember we were talking about Golgi tendon organs, right? Golgi organs are there. They live in the tendon. So I've got a Golgi tendon organ that lives in my tendon right here, right? And their job is to sense how much tension there is within a muscle. And so whenever there's too much tension, you remember, like, tension is caused by overstretching a muscle, right? So if you have something that's overstretched, what should you do? You should unstretch it. You should contract it. You should make it shorter instead of letting it get longer. So when you smack this Golgi tendon organ really hard, what happens is your nervous system gets kind of fooled into thinking that you just stretched your quadriceps like crazy. Like when you smack that tendon, what it thinks is happening is you're doing this, but like at the speed of light. You know, like it's like your brain is getting confused, thinking that you just tried to rip your foot like around your body, you know? And so what it's doing to protect itself is it shortens the quadriceps muscle. It squeezes it as a protective mechanism. And that is, whenever you squeeze this muscle, what happens is your leg kicks forward. So when you go like this, I'm gonna try and like hit it here. Yeah, that was not bad. I usually miss it. But when you smack it, you'll get like a small, you know, little kick. And that little kick is basically your Golgi tendon organ going, whoa, you know, and it contracts really, really, really hard. Now that's a stretch reflex. Remember earlier I mentioned stretch reflexes. When you smack that, you're seeing a stretch reflex in action. So yeah, absolutely, that's totally what that is, Noel. By the way, I gotta ask. I think I asked yesterday, but I think I might have had you muted. Is it? Do you prefer? Am I supposed to pronounce it Noel or Noel?
Either one. I go by Noel, really. But
Noel. Okay, that's.
yeah,
I want to
but
go.
if you
I want to
say
say.
Noel,
Yeah.
you can say Noel, man.
No. I want to go by what you prefer. Make me adjust, not you. That's Noel. Okay. Because yeah, here's it's I got the same thing. Like my name is weird fun. Yeah, my name is Brad. My middle name is Lee. So when people call me Bradley, I'm always like, nah, it's not my name. My name is not Bradley. My name is Brad Lee.
And they just put it all together. Huh?
Yeah, my parents were lazy. They couldn't figure out a middle name, so they cut my name in half. All right. Okay, so let's go ahead and dive back into it here. So that's what a stretch reflex is, and that's what a tendon is, right? So this right here is where the Golgi tendon organ is going to live. And then Irene, you were asking, does it ever look like ligaments? Yeah, absolutely. I mean, look right here. You can see by the way, there's the IT band. See how all that fascia coming down from right here? There's your IT band, and then it's going to grab onto the tibia on the side there. This is why your IT band, surprisingly, I know it's on the side of your leg, but it actually acts as a hip flexor because it may run along the side, but it attaches in the front. And then you can see, look at all these little off to the side here, these little white bits. That's like your lateral collateral ligament and your medial collateral ligament, right? Your medial on this side and your lateral on this side. And so we look at ligaments versus tendons, and we'll look at the knee. We'll pull up the knee here. You can kind of see all of them kind of coming together. Yeah, that's a good one. They all look similar because they're all drawn in white here. But see, this is like a little tiny ligament off to the side. But then see how the muscles ending in it kind of turns this whitish color. That's the tendon portion. So they do look really similar. And yeah, Irene, they will be in super similar spots. But they are two totally different types of tissue. You aren't going to find Golgi tendon organs living in a ligament, for instance. But you'll find what are called Pacinian corpuscles. It's a fun, weird word to say. Okay. So those are all, that's kind of our layers there. We've talked about layers. We've talked about how our muscles end in a tendon. Now we got to kind of get onto a cellular level here. So now we need to zoom in like crazy, and we're going to get into the most technical part of probably this whole course, if I'm being honest. Just in terms of a lot of small moving parts here, and honestly, we can't really see any of them because we don't really, we're not working with microscopes here. So we got to get into our cellular bit here. So I'm just going to pull up just before we get started, do a quick refresher on cells in general, animal cell. All right, let's just take a look at a really basic animal cell. This is how you always draw them in class, right? Whenever you see an animal cell in a textbook or something, what's funny is you don't really have any cells that look like this. This is just kind of like a generic, cell that's really easy to understand because it's got all the parts, right? So here's a cell, right? It's got a little wall around the outside. In the dead center, you've got a nucleus, right? It's in charge of housing all your DNA. Inside, you're going to see things like these little guys. These are called lysosomes. They're like your immune system for your cells. They're eating and dissolving anything. You're going to see mitochondria here, and here. They're there to produce energy, right? So those are really, really important. Those are our energy makers. You can see this is pointing to nothing, but there is a bunch of fluid inside the cell here. That fluid is called your cytoplasm. You've got this stuff here, which is called your ER. That stands for endoplasmic reticulum. You've got smooth and you've got rough. The rough has all these little ribosomes that live on it, which are these little tiny dots here. Their job is to assemble all the proteins that your nucleus sort of tells them to assemble. Remember, the nucleus is like the brain. It's got all your DNA, and it says, hey, this is, it's got a blueprint. It's like, this is what the body's supposed to look like. And the ribosomes are like, got it, boss. And then they assemble it all. And so that's kind of what this whole thing sort of looks like. That's a classic animal cell, okay? You don't need to know most of those terms right now. You don't need to know most of those terms right now. Let's look at a muscle cell. So a muscle fiber, remember I mentioned function follows form. So your muscle cells have to have a special function, which means they need to look a certain way. They have to have an interesting shape to them. And so they do. Like, for instance, take a look right here. You can see, oh, that's actually great. Look at that. That's an even better picture because you can see the actin and the myosin there. Hold on. Not quite getting what I want. Look at that dude. God dang it. Muscle fiber, muscle cell. How do I do that? That's closer. All right, we'll go with this one. I just don't like this one because it's low quality. Ah, there we go. All right, so let's look at our muscle cell here. See all this, like, when you look at it, right? On the inside of an individual like little muscle fiber, you are gonna see all of these little tiny bands. Do you guys see these? Like, see how like there's like the little like thin red lines, and then there's all these like little thin blue lines? Those are actually proteins because we're still zoomed out really far in this picture. I know we're zoomed in like crazy, but we're still technically kind of zoomed out. And so that is what we're looking at there. That area where they're crossing over each other is really important. This area is actually what allows a muscle cell to contract. And you can see if this muscle cell contracts, it can contract at the same time as this muscle cell, and at the same time as this muscle cell, and that one, and that one, and that one, and that one, right? This whole thing is a fascicle, right? It's a whole bunch of individual, there's a muscle cell, there's a muscle cell, there's another one. All those muscle fibers are bound together, right? So when we look at it, right, you can kind of see it here, right? This muscle cell is attached to that muscle cell, which is attached to that one, attached to that one, that one, that one, and it's all wrapped together in a fascicle. And then, that's going to be wrapped together with a whole bunch of other muscle cells. Now, inside, remember I mentioned earlier, you've got your, actually, hold on, before we get into that, that area, by the way, the area where they are crossing over each other, like this is a section of town, basically. Think of it that way. This isn't something physical that you can hold, but it's an area. The area where these proteins are crossing over each other is called the sarcomere. Sarco is a Latin prefix, and it stands for flesh. So anytime you hear the word sarco, you are in muscle territory. We're talking about muscles. Whenever you hear the word sarco, just start thinking muscles. Whenever you hear the word myo actually means muscle. That's another one that knows you're in. So if you ever hear the prefix myo something or sarco something, we're talking about muscles. So I'm going to keep this picture up because we're going to come back to it here in just a second. So function follows form, right? Muscle cells look a little bit different compared to other cells. That classic animal cell that we pulled up earlier, remember I mentioned you've got that endoplasmic reticulum. It's there to like have the ribosomes live so that they can assemble the proteins. In a muscle, you've got this stuff right here, this kind of blue webbing that's sort of covering everything. That is actually what's called your sarcoplasmic reticulum. And so it's a special version that looks slightly unique of endoplasmic reticulum. And it's special because it does something that traditional endoplasmic reticulum doesn't, in the sense that like, it's really not endo. It's not on the inside. It's actually on the outside. And it allows materials to travel around through these things, these little little spots here, which are called T-tubules, that actually allows materials to travel around the muscle cell. And that way I can get like a little bit of, calcium, which is actually what allows my muscles to contract. I can get it from one area to the other, and it can get where it needs to go to create that contraction. It's like a highway system surrounding throughout your muscles. So let's go ahead and go through all of the components that you're going to find that are slightly special inside of a muscle cell, compared to like a normal cell. So one of the things, remember earlier I also mentioned you got the fluid, the wet soupy mixture inside your cells. That's called your cytoplasm in a normal cell. In a muscle, because we're talking about muscles, right, we're going to call that the sarcoplasm. Sarco for flesh. So it's the flesh fluid. Gross. So that's the liquid portion of your muscle cells. It's going to have some glycogen in it. It's going to have fat, minerals, things like myoglobin, right? Myoglobin is that special protein that carries oxygen in muscles, right? Instead of hemoglobin, which is the special protein that carries oxygen in blood cells. By the way, and this is mostly just for you, Noel, the only reason I'm using a lot of terms here, and as if you just like instinctively know them, is because we've been through them in other classes. A lot of these are not important to know for this current course, but you will come back to them later. In like myoglobin becomes really important in like our cardio class. But we're not spending too much time talking about myoglobin in this course. So the sarcoplasm is the fluid within your muscle cells, right? Now, your muscle cells are totally still going to have a nucleus, right? So you've got nuclei in there. That's the brain for your cells. You definitely got mitochondria, right? Mitochondria, I hate to say it because I sound like a high school biology teacher ever, but they are the powerhouse of the cell. Their job is to take in things like glucose and oxygen and spit out a whole bunch of energy. So they transform the energy from food into energy for a cell. And so that's your mitochondria. You get tons of them in your muscles because your muscles burn more energy almost than anything else in your body, with the exception of your nervous system. And then here's the part that's actually important, especially for this class. And here's my, if you forget everything, actually we got two sections that are really important today. But if you forget, I'd say this is the second most important. If you forget everything from today's lesson, you remember two things. This is the second one. Myofibrils or myofibrils. This right here is the probably second most important part of this lecture. So what are myofibrils? Those are things that are called, they're going to house what are called myofilaments. And the myofilaments are the actual contracting part of a muscle cell. So when you look at this arrangement, right, if you zoom in on the inside of a muscle cell, you are going to find these special little things called myofibrils. So this picture here, you can kind of see this area is the sarcomere, right? That's your sarcomere there. And when you zoom in on a sarcomere, what you're going to find is you zoom in even further, you'll see those little red lines and those little blue lines. When you actually zoom in on them, they actually look like this. And this is the most important part here, right? You can kind of see that little arrangement, right? I'm going to go back to paint here. They're arranged like this. Oh, God. You know what? Actually, wait, there's a line tool. They're arranged like this. And what can happen is this stuff can move this way, and this stuff can move this way, and this stuff can move that way. Oh my God. And so your muscle can go from, being this long to being this long. and then it can relax. So these little proteins right here, right, this area where they're overlapping, right, that area is arguably the most important part of that's what makes your muscle cells able to do this totally unique thing that all other tissues in your body can't do, right? That is what makes muscles totally unique. So let's label all those out so that you know these proteins, because they are going to ask you about this on your tests. So your myofibrils contain your myofilaments, right? So your myofibril is sort of the whole section, and the myofilaments are this guy right here and this guy right here, right? And so of your two myofilaments, one of them that you definitely want to have in your notes is actin. So actin is the thin filament that is responsible for muscle contractions. Myosin is the middle one here. That is the thick filament responsible for muscle contractions, right? So you've got thin filaments and you've got thick filaments. And here's the thing. Look at the thick filaments, right? Look at this guy. See all these little like fuzzy, they almost look like fuzzy things reaching off of them, but they're little like club, like little heads, right? Well, your myosin, which is this little thin filament, it has a whole bunch of little like slots for those heads to reach up and grab. And so when you look at it, I'm going to go back to paint here. Where is the brush tool? Right? Yeah. When you look at it, it kind of looks like this is what actin looks like. It's got all these little binding sites. It's this really thin little filament that has all these little binding sites, right? It's usually about 2 layers. Right? And then there's the thick filament that looks kind of like this. It's got these little, they almost look like music notes. They reach up and they've got all these little club-like heads. And those heads really want to reach up and insert onto that and pull it this way, right? So it wants to reach up and grab it and pull. So let's take a look at that. I'm sure I can find a GIF for this. Actin and myosin GIF. There we go. So there you go. See how these little heads are reaching up and they're grabbing? And look, they're pulling end to end, and those ends start coming closer together. This muscle is shortening. That's a muscular contraction. All these little heads reaching up and pulling. So the video, or the analogy that everybody likes to use when they're teaching this is kind of like a Romeo and Juliet situation, right? 2 teenagers absolutely in love who want to get all up in each other's business, right? And so this little head here is super attracted to the binding sites found on actin, right? So myosin is super attracted to actin's binding sites. So what it wants to do is it wants to reach up. Oh my God, this GIF is so slow. It wants to reach up, grab it, and then it wants to pull like that. And then that's how a contraction actually happens, right? So it's going to burn up a little bit of energy here and then move those binding sites. Now the binding sites are exposed, and it's going to reach up, grab it, and pull it this way. Shoomp, right? And that is actually a contraction taking place in real time. So actin is a thin filament, and you'll notice we wrote it in our notes here. It has binding sites that myosin is attracted to, right? It's weird to get all up in the analogy land here, but basically Juliet here is very attractive, and Romeo wants to get all up in her business. So it's very attracted to it. Now here's the thing. We don't want this to happen all the time because they are so attracted to each other. Actin and myosin, if they could bind together, they would bind together and they would never let go. And that's not what we want, because then we would be stuck in whatever position. Here's a weird fun fact to kind of describe that. That's actually what rigor mortis is. You guys ever see the movie The Ring? It's a horror movie. They watch like a videotape and it kills them. In that movie, whenever somebody like finds like a dead body, they're all like, they're all contorted and stuck like that. That's what's called a rigor mortis, and it's where our bodies. This is actually why we also call a dead body it's like they call it a stiff. And so the reason they call it that is because what happens is your body's actin and myosin proteins contract together and then they get stuck that way. And so our body kind of gets contorted and stuck in a position because there's nothing to keep those two from binding to each other, and nothing to cause the muscles to relax. After a while, it'll relax, but in the initial stages of being a dead body, that's kind of what happens. So there's your weird fun fact to remember for a day. If they had their way, actin and myosin would be bound together all the time and our muscles would never relax. So we don't want that to happen, right? We want to have the ability to relax our muscles. So luckily we have what are called regulatory proteins, and they regulate when actin and myosin can bind together. Those regulatory proteins are called troponin and tropomyosin. They're regulatory proteins that block myosin from reaching up and binding to the actin. So you can actually see that in this picture here. Do you guys see the little blue bit here? Can I make this bigger? I can. Okay, see this little blue bit right here? And you see this little like line right here, right? And then see how that just moved out of the way? That is the regulatory proteins getting out of the way. And now the binding site is exposed. So because it's exposed, myosin binds to actin and it pulls it, right? So right here, this is troponin and this is tropomyosin, the big band here. And the band is what's blocking the binding sites. And so basically they're like chaperones at an 8th grade dance being like, hey, 6 inches apart, you know, like none of that, none, don't, you know, get all up in each other's business. They're chaperones making sure that contractions don't happen when we don't want them to happen. So when your muscles are relaxed, the chaperones are in place. But when you want to create like a muscular contraction, the chaperones move out of the way, right? Troponin and tropomyosin move out of the way, and then myosin reaches up, grabs actin, and pulls it. And that's what we're seeing in a muscular contraction. So that's what we're looking at, right? You've got actin, which has binding sites. You've got myosin, which have heads that bind to those binding sites. And you have troponin and tropomyosin, which block those binding sites. When troponin and tropomyosin aren't in the way, myosin gets all up in actin's business and creates a muscular contraction. And the area where all of that happens, right? The area from here to here is called the sarcomere, right? That is the space between two of those lines where they cross each other. And so the sarcomere is the actual, like when we say the functional unit of your muscular system, thanks to having this special area within muscle cells, that's what allows muscle cells to have this totally unique function, which is to contract and relax. No other cell within the body has that ability. It has to have like, that's what, when they say like something is a muscle, that's what we're talking about. Whether it is skeletal muscle, your heart, or even just like your digestive system, squeezing stuff through to get it to, you know, pass around through your whole digestive tract. All those little contractions are taking place because there's sarcomeres within those special types of cells. So, here's what that kind of looks like if we zoom out just a little bit, right? You can see here is that really thick filament, right? That's the myosin. And then here's the little thin filament with all the binding sites. And what's going to happen is when you have a relaxed muscle, they're totally not crossing each other, right? You see a relaxed muscle here, the muscle's nice and long, and there's plenty of space. But then you see a partially contract, and then you see it's kind of going through a contraction here, right? Now what's happening is, you know, the actin is, this actin over here is getting pulled this way, and this actin over here is getting pulled this way. And eventually they're going to get closer and closer. So here's like a relaxed muscle, here's a partially contracted muscle, here's a fully contracted muscle, right? Until eventually they can't contract any further. And look, your muscle literally bulges like this. It actually bunches up, right? Like it goes from being nice and long to being really bunched up, and then it goes back to being nice and long, and then it goes back to being bunched up, right? It goes and squeezes like that and kind of bunches up. That's why we have all that fascia I mentioned earlier. When it's bunched up like that, we don't want those fibers crossing each other and getting tangled. So your fascia is there to keep that from happening. So I want to show you one more time, just really quickly. I want to show you what I mean when I'm talking about like a muscle that's like fully contracted versus like not contracted at all, right? So you would have like a thick myosin filament in the center that might look something kind of like this. So there's our myosin. I'm just gonna keep that kind of simple. And then let's look at, you would have your actin strands. They would be kind of like this. A really thin filament, right? That's not gonna work. So that's a relaxed muscle. But then you would have a fully contracted muscle that might look something like this. If it's a fully contracted muscle, oh my God, it would look something like this. And see how it's, there's really not much more space to move. That's because it's contracted. Now, here's the thing. For those of you who, I've talked about this before when we talk about posture, right? See how there's not very much space to move here? Here, there's tons of space to move, right? But here, there's very little space. In overactive muscles, and Noel, we haven't talked too much about overactive, underactive muscles yet, but Robert and Irene, we've talked about this a lot, and anybody watching this recording who's been through this, when I say a muscle is overactive, this is kind of what it looks like. See how there's really not very much space to move, right? It's already partially contracted. Let's say you have a client who's got elevated shoulders, right? They just spend, you know, a lot of time, they're just tense, right? They hold like a lot of tension up here, right? They generally have this kind of forward, maybe hunch over thing. This is what they sort of look like. My roommate is like this, right? Well, what's happening is this muscle is just in a shortened state automatically. It's just elevated here. I actually have a little bit of this. If you look, do you guys notice, if you look at like my shoulders, do you notice how my left one is ever so slightly higher than my right? This muscle is slightly more overactive than this side. And that is where this muscle is somewhat partially contracted, and then the other one is partially relaxed. And so when you talk about like an overactive versus an underactive muscle, this is where a lot of times like we'll simplify it down and we'll be like, oh, you got one muscle that's too strong and you got another muscle that's too weak, right? You got one muscle that fires too much, that's the overstrong one, that's the overactive muscle. You got one that's not firing enough, it's weak, that's the underactive muscle, right? And it's like, I mean, I like using that description with my clients because it's really basic and easy for them to understand, but that's not 100% accurate. Overactive muscles aren't necessarily stronger muscles. They're weaker than they should be because they're already in a partially contracted state. They can't contract anymore, so they're actually losing force production. And underactive muscles, because they're so pulled into a lengthened position, they can't get a good grip. Actin and myosin don't have enough overlap, and now they can't contract as strong as they're supposed to. So when you have an overactive, underactive muscle, it's not 100% true that you have one strong and one weak. You have one that fires harder and one that fires weaker, but they both are weak. They both are weaker than they should be. Does that make sense? There's less troponin. Not necessarily. No. The troponins, the amount of troponin is the same, but in an overactive muscle, the binding sites are already bound, and so troponin can't get back into place. But it's still there, like structurally. It's not that there's less of it. Good question though. That's a great question. Yeah. Yeah, it's not that there's less troponin. It's just that the muscle is like, nah, we're gonna be together. We're making out. Go away. All right. Questions about this whole section. How you guys feeling about actin, myosin, and things like that. Do we need to spend a little bit more time on this? How you guys feeling?
Feeling good, man. But once I hit the notes, I feel like I'm gonna get it more. You know what I'm saying?
Yeah. We're going to revisit this
we get the
almost
quiz.
every module. We're going to revisit this concept almost every module. So, you know, if you don't get it on this first round, you're definitely going to get it on the second, third, or fourth.
Yeah.
All right. So let's go ahead and zoom down. We got to get a little more complicated with it. So we're not done yet. All right. So how the heck do you trigger this binding and unbinding? How do you make these contractions take place, right? We know that your muscular system is under the control of your nervous system. So how the heck do I, you know, we see this whole thing here. How do I make this happen? How do I make the contraction actually occur? Well, that is where we have to kind of pivot our conversation and start talking about our nervous system. So I'm going to keep this video up because it's actually going to come back here in just a second. So neural activation. This is where we start calling it your neuromuscular system, right? It's the contraction of a muscle generated by neural stimulation. So neural activation is the link between your nervous system and your muscular system. And it's where you have these motor neurons, right? We have our three types of neurons: sensory, interneurons, and motor neurons. It's where a motor neuron travels from the brain and it zaps a muscle and gets your muscle to go, you know, and contract, right? And so we call that a motor unit. This is one of our most important terms here. A motor unit is a single motor neuron, right? So a motor neuron, and all of the individual fibers that it, what we say, innervates or zaps, right? So let's look at a motor neuron here, right? That's actually not what I want. Motor unit, sorry. GIF? Yeah, motor unit GIF. All right, I'm back on the GIF train. So you would have a single, you know, motor neuron, and then you'll notice it travels down, and it's got three little fingers here. Each of those fingers are attached to different muscle cells, right? We're drawing, those muscle cells look very different than the other pictures we were looking at, but that's what we're talking about, right? You'll notice how this motor neuron splits off into all kinds of individual fibers, and it zaps a bunch of different muscle fibers simultaneously, right? So you might have one neuron, but it's zapping, you know, however many individual fibers, you know? You've got big motor units and you've got small motor units, right? But basically, what a motor unit is it's a motor neuron. They are attached to muscle fibers, and when that neuron is excited, or when it zaps, it will innervate all of the muscle fibers that it is attached to. So when we talk about like generating force in a muscle, right? When we're talking about that, we're talking about like your nervous system zapping a muscle to get it to contract, right? And so that whole process is pretty complicated. It does it through a series of electrochemical signals, right? So one neuron would zap, let's say 50 fibers, right? Or maybe it's like, that's what makes, you know, the difference between like a strong contraction and a weak contraction. The more fibers that I recruit, the stronger my contraction is going to be. So like I said, this is going to take place because of electrochemical signals. So the chemical that's allowing this to take place is, we call it a neurotransmitter. It's called acetylcholine, or ACH. And that's the one that's actually responsible for triggering this contraction. So what'll happen is an electric impulse is going to be transported from the central nervous system down the axon of a neuron. And when that impulse reaches the end of the axon, neurotransmitters, acetylcholine, are released into the area between the neuron and the muscle fiber. So it will contract, it'll move across, and then it's going to bind to the muscle. And once it binds to the muscle, that's going to create an action potential. That's going to create an electricity signal traveling throughout the muscle to get it to actually fire. And that's what we're seeing here, right? And so we talk about like the whole process of like the sliding filament theory. that is where actin and myosin are sliding across each other, right? They're contracting, moving from this side and this side, making that muscle shorten. That is a sliding action that takes place. And it takes place because your nervous system zaps this muscle by releasing this chemical, acetylcholine, to create an electric potential. Yeah, kind of like Wi-Fi. Yeah. So signals like traveling to get it to actually happen. So here is a very, very wordy PowerPoint, but this is basically what's happening whenever you get like a contraction. So an action potential, nerve impulse, right? Electricity is traveling from a neuron where it will meet a muscle fiber, and it will release this neurotransmitter into the muscle fiber, and it'll bind to a receptor site on that muscle fiber. Then that muscle fiber will release, and this is the surprising part for some people, it will release calcium into that wet goo, that sarcoplasm, the fluid portion of the cell, right? And it will release that calcium into the sarcoplasm. And remember earlier I talked about how the chaperones, they're blocking those binding sites. How do we get those chaperones to move out of the way? That's where calcium comes in. So you release a bunch of calcium into your muscle, and troponin and tropomyosin, those chaperones, they can't resist it. They're like, it's like buying off the chaperones, right? They're like, all right, now you two, you're not allowed to contract. Don't contract while I'm gone, but I'm gonna go see what this calcium's all about. Like, and then it moves out of the way. And actin and myosin are like, oh, we're gonna get together, right? Like, and then the contraction takes place. So acetylcholine causes an action potential to travel around a muscle. And when that action potential travels throughout the muscle, it releases any stored calcium that it has into the area. That calcium causes troponin and tropomyosin to move away. Now the binding site is exposed. And so myosin is like, it's on. And it gets up there, grabs actin, and slides, right? So that is how you can see in this GIF here that I was pulling up earlier, right? We're gonna wait for this GIF to kind of reset, but like, look, the binding sites are exposed and it contracts. Now, here's the thing. You see these 4 little circles right here? That is calcium. So calcium binds to troponin, it moves troponin out of the way, troponin and tropomyosin. Now the binding sites are exposed. So myosin reaches up and grabs, and then it is going to slide. And then eventually calcium will detach. That will put the binding sites back into place, and the muscle will relax. And the whole process will start over and over and over again. And that is muscular contractions on a cellular level. So you wouldn't think it would be so complicated, but there it is, right? There it is happening. They're gonna reach up and bind, and this is kind of a 4-step, just a big circle. It happens over and over again, right? This is gonna reach up and bind, it's gonna slide, and then it will relax back into place. So it goes from here to here to here to here to here, right? Over and over and over and over again. Now, one thing that's fun to remember, and this is one of my favorite concepts, I just think this is so cool. There is a principle in the world of biology called the all or nothing principle. And what the all or nothing principle states is that regardless of the number of individual muscle cells, individual muscle fibers, when a motor unit contracts, it always contracts as hard as it can. There is no such thing as a muscle cell creating a weak contraction or a strong contraction. Your muscle fibers contract fully or they do not contract at all. Now that seems really surprising because you're like, well, wait a minute, like I can pick up like a cat and I can also like throw a baseball. Those are 2 totally different contractions, right? One is really large, one is really small. So how is it that you have big contractions and weak contractions? Well, that is because you will either recruit lots of muscle fibers or you will recruit very few muscle fibers. So you'll recruit like a large motor unit or you'll recruit a small motor unit. Remember, a motor unit is 1 neuron and all of the fibers it innervates. Sometimes it innervates thousands, and sometimes it innervates 10 to 20. So if it's doing 10 to 20, that's a small contraction. All of the fibers are contracting as hard as they can, but it's still a relatively weak contraction because there just isn't that many fibers being recruited. But if it is a really strong contraction, you're recruiting as many of them as they can. And this is where Irene and Robert and anybody who's been through program design, and we've talked about max strength phase before, this is where you'll remember what are we training for in max strength? Where we're training for motor unit recruitment, motor unit synchronization, and motor unit firing rate, right? Those two we'll talk about later. But like that recruitment part is like you're training your nervous system to recruit as many fibers simultaneously as possible. How do we do that? We lift lots and lots and lots of weight. We make it as heavy as possible. And that's what results in maximum strength gains. So the difference between a strong contraction and a weak contraction is the number of motor units that are being recruited. Oops, I got ahead on the notes, but that's what it says in this slide here. Oh, and here's a fun one. I forgot this is in here. So how many muscle fibers are contained within a unit is what's going to affect the strength. Precise movements are made of small motor units, like 10 to 20 fibers, right? So like the muscles in your eyes, right? You know, I'm not doing, you know, curls with my eyes. So you got about 10 to 20 muscle fibers that control your eye moving around. But if you look at like a large muscle fiber, like your calf, it's got 2,000 to 3,000 motor units. And you got like 8,000 to 10,000 in your glutes. That's why it's the money maker. Biggest muscle in the body.
I got a question.
Yeah, question. What's up?
Hey, so if you're doing bench press, right?
Mm-hmm.
You doing more reps. Would it equal out as strength? You getting stronger if you doing less reps with more weight?
So here's the thing. You will get stronger, but you will not get maximally stronger. So there is a difference between like an endurance style of strength, a muscular growth style of strength, and maximal like get something from point A to point B strength, right? Like I can lift 1,000 pounds once, you know, like that's maximal strength versus like, oh, I can only lift 600 pounds, but I can do it 20 times. I don't know why I picked such large numbers. But like there's one that's like an endurance style of strength. There's also one that results in like lots of cellular growth. And there's one that results in like maximal strength, like, which is literally just like one and then you rack it, you know? And they are different from each other. So they don't really affect.
So it's 3 phases.
Yeah, it is 3 phases actually. And that is actually what they're called too. I don't know if you've already picked forward in your book, but yes, there are 3 phases. And so the strength and the endurance style, right, is concerned with like heavy, but like lots of repetitions. The hypertrophy style is kind of like a cross between lots of repetitions and very little repetitions. So it's kind of in the middle there. It's like lots of reps, but also high intensity. So it's really in the middle. And then you've got like the maximal strength gain, which is really, you're not really growing, like you're not really focused as much on growing muscle. You're really just focused on training your nervous system. You're teaching your nervous system how to zap as many fibers as possible. And the way you train for that is you lift super heavy, like 1 to 5 repetitions. You want to get muscular growth, you're going to go somewhere from 6 to 12 repetitions. You want to get muscular endurance, you're going to go somewhere from like 12 to 15 or 12 to 20 repetitions. Does that make sense, everybody? That was a great question. And insightful.
So Brad, to get the chaperone out of the way, it's only calcium that binds onto troponin.
Yep.
What happens to, like, go ahead.
Oh, I'm sorry, I interrupted you. What was the rest of your question?
No, yeah, that's it.
Yeah, so it's just calcium. So what happens is acetylcholine travel, like the neuron gets like an electric impulse. So an electric impulse starts at your brain, and then it goes from neuron to neuron to neuron to neuron to neuron to neuron until eventually it gets to a muscle, right? And then the way that your nervous system interacts with your muscular system is it releases, because it can't just like zap it with electricity. It has to zap it with a chemical instead. And so the neuron releases acetylcholine, which then attaches to a muscle. And that tells the muscle, you need to now make electricity. So then your muscle creates an electric action potential that travels along the whole muscle fiber. And that electric signal releases calcium into the area. And now that there's calcium in the area, tropin and tropomyosin are like, that's great. And they move out of the way. And when they move out of the way, the binding site is exposed and the sliding happens. And then what you'll do is you'll burn up a little bit of ATP, and that will flush all the calcium out of the area. The binding sites will go back into place, and the muscle will relax. That clear it up?
Yeah, and that takes place in like milliseconds. Like
Yeah. Yep. Yeah,
Okay.
it's at the friggin', you know, I say, I mean, I don't mean this when I say this. Yeah, it's happening at the friggin' speed of light, you know? Obviously, it's not happening that fast, but it's really fast. Yeah, super fast. About like earlier when we were looking at this in the nervous system earlier, what was it, 2 days ago? About 1 to 22 milliseconds. So, all right, let's zoom out. Right? We've been zoomed in forever. Let's zoom out a little bit. All right, let's look at our different types of muscle fibers, right? So like one of the differences between like men and women, for instance, right, is men tend to have like a higher propensity for type 2 muscle fibers. Now, the thing about type 1 and type 2 muscle fibers, they're not technically different types of tissues. They just look slightly different. So we just label them based on like how they look. So when I say like something is a type 1 fiber and a type 2 fiber, I'll bet there's two people who could totally argue about which one's type. Like if you were to pull a muscle fiber out of the body and look at it under a microscope and put two scientists and both of them analyze it, they might have a different opinion. One of them might say, I think that's a type 1 fiber. Look at how much mitochondria it has. And the other one would go, oh, I think it's a type 2 fiber. Look at how many proteins it has. There could be a total argument here. So this, when I say something is type 1 or something is type 2, it's not like a hard line, right? This isn't like a hard line situation. It's just that they have characteristics that make them a little bit different from each other. So your muscle fiber types. Muscles vary in terms of their chemical and mechanical, like physical makeup, and that gives them different characteristics. So the two major categories you've got are type 1 and type 2 muscle fibers. Type 1 fibers are what are called, sometimes they're referred to as red fibers because they get lots of blood flow, so they tend to be a little more like darker stained red because there's just more blood running through them over the years. And so type 1 fibers are, like I said, sometimes called red fibers, but they are smaller in size generally, and they're used for long-term endurance type contractions. So Noelle, you were asking about like the difference between high reps and low reps. If you were doing high reps, you would be primarily focused on training your type 1 slow twitch muscle fibers. These are often the fibers that are associated with like stability and like controlling your body. So like when I stand on one leg, right, I can do this for a real,
like the core, right?
Yeah, perfect, right. Like your core is a type 1 situation. It's there, it's keeping you upright right now. You may not feel like you're like, you know, contracting your core like crazy, but your core is contracting right now to keep you upright. That's a type 1 situation. Your calves, well, they're kind of a cross between the two. They've got a lot of ability to kind of, you know, I could do this for a couple hours, you know, probably. Now, that's maybe an exaggeration. But I can do it for a real long time, right? This is a type 1 situation, right? Versus like a type 2 situation, which is where like you get your fast twitch fibers, right? And fast twitch fibers are often called white fibers because they are larger in size. They don't get as much blood flow, so they don't recover quite as quickly, which means like a lot of times they'll get exhausted and they'll kind of stay exhausted. Whereas red fibers tend to like get a lot of blood flow, so they're like, we're tired, we're recovered. We're tired, we're recovered, right? Like they tend to like be able to just keep going and keep going. They're like the Energizer bunny of fibers, right? Whereas type 2 fibers are what we think of when we think of like strength training, right? You know, your shoulders have a great ability to kind of hold you up for a long time. those are recruiting the type 1 fibers in your shoulders. But you've also got like some heavy lifts that you can do with your shoulders. Those are the type 2 fibers. So you're going to have like a mixture throughout your whole body. It's not as simple as like your glutes, you know, are type 2 fibers. Even though this is the strongest muscle in your body, yeah, it's primarily type 2. But you use your glutes during a marathon. So, you know, there are definitely type 1 fibers in there that can run for hours at a time. So this is what we often associate. Type 1 fibers are slow twitch, type 2 are fast twitch. The reason we're breaking this down is because you're going to have athletes that have different needs. If I've got an athlete who's primarily on the field for a couple hours, I'm probably going to put some emphasis on their type 1 fibers, but I don't want to neglect training type 2 because who knows, maybe during that athletic event, they need to have a big burst of energy where they recruit a bunch of type 2 stuff. So this is where we get into where we start to kind of split type 2 into two smaller like subcategories. So type 2 fibers are often associated with power and force. And within that category, you're going to have type 2X muscle fibers, and you've got type 2A muscle fibers. Type 2X, X stands for extreme. No, it doesn't. But it stands for intense, right? It's oxidative or low oxidative. So your type 2X fibers, they are the true fast twitch fibers. They're like, ah! And that's it. Like they need a nap after that. So these are fibers that are super explosive and then need a ton of time to recover. Your type 2A fibers are kind of like straddling the line between type 1 and type 2. They don't have as much mitochondria as a type 1 fiber, but they aren't quite as like powerful as a type 2X fiber, but they're fairly powerful. They've got some mitochondria, and they're still somewhat large in size. So they fatigue much more slowly compared to type 2X. This is where, like, when you look at like pro athletes, right? You would think that an athlete, you'd want them to be absolutely crazy as explosive as possible. And it's totally true. We do want our athletes to be super explosive, right? But when we're training them, we want them to be super explosive compared to anybody else in that sport. But like, I don't need a football player to set the world deadlifting, powerlifting record. You know what I mean? Like an NFL player that can lift as heavy as like Eddie Hall, you know, like, which will never happen because freaking Eddie Hall is a monster. You know, Eddie Hall, very famous powerlifter. He had the world record for the deadlift. It was broken by Thor Bjornsson, the guy who plays the Mountain on Game of Thrones. Recently, like I think earlier this year or maybe at the end of last year. Anyway, that doesn't matter. I don't want an NFL player who can break their record, because if he's spent all that time training for a super heavy deadlift, he may be super explosive, but I know that he hasn't been training for endurance. And so I can put him out. Maybe I want him for one play, and then he has to sit for the rest of the game. You know, like that's not really all that handy. So we really want to train most of our athletes with type 2A fibers. We want them to be way stronger than type 1 fibers, but we also want them to have plenty of endurance. And that's why, like, you look at some of the incredible feats of strength that like a pro basketball or a pro football player can do. You know, they're heavy compared to like a lot of people, but they're never going to be as heavy as like people who are like true power lifters, but they're also not going to be as light as somebody who's like a runner, right? Does that make sense to everybody? So yeah, athleticism, we focus on 2A fibers generally. We want them to be strong, but we also want them to have endurance. All right. So here's some of our characteristics, by the way. You can see type 1 fibers, they have more capillaries, meaning they get more blood flow. Because they have more blood flow, they get more oxygen delivered. So they're going to have more mitochondria, which is spelled wrong in this PowerPoint. They're going to also have more myoglobin. They have increased oxygen delivery. They tend to be smaller in size, and because of that, they're going to produce less force. But even though they might not be able to produce as much force, they are very slow to fatigue. They are used for long-term contractions, right? Versus your fast twitch fibers, which they don't have as much blood flow, which means they don't have as much mitochondria, which means they don't have as much myoglobin, which means they don't get as much oxygen delivery. So they're going to repair and recover a little more slowly, but they are much larger in size. They have way more actin and myosin fibers. They produce more force, and they're very quick to fatigue, but the amount of force they're able to produce is much, much higher. So a type 2 fiber will be able to jump higher than a type 1 fiber, but a type 1 fiber will be able to jump more often than a type 2 fiber. All right, so that is sort of our muscle fiber types. Now, last little thing we're going to look at, and these are going to be some of, remember I said the most important thing you're going to learn today. This right here at the end is the most important part of today's lesson, because these are terms we are going to use for the rest of this course. So I'm going to read this whole slide here, which I normally try not to do because that's very boring for you guys. You can read slides yourselves. But muscles provide the body with a variety of functions that allow them to manipulate forces placed on the body and produce movement. These roles, these functions, are categorized as an agonist, synergist, stabilizer, or antagonist. So muscles can act in any of these roles. That's one thing you got to remember. There's no muscle that is only ever an agonist, right? It's an agonist in one situation. It's an antagonist in another situation. It might act as a synergist in another situation. So muscles can act in any of these roles depending on the movement. So I love this little quote here, but keep in mind that in this course of one simple action, a muscle's role can change. It might begin the movement as an agonist and then quickly switch hats to become a fixator or finish as a synergist. I actually don't teach you guys fixators. Fixators are muscles that sort of allow, like when there's like a transfer of power from one direction to another, they kind of hold it in place. It's a term that never really has to come up. Muscles as movers, right? Let's talk about like what a muscle is when it is an agonist. So an agonist is a prime mover. It is the muscle that primarily moves a joint in whatever direction it's going. So for instance, if I'm describing the motion of hip extension, which is this, right? I'm doing hip extension. This is hip flexion. This is hip extension, right? I need to lower that down just a little bit. So when I'm doing hip extension, my glute, my butt muscle, is mostly in charge of this motion, right? I'm going to keep my leg nice and straight, but that's pure hip extension, right? And you can feel it. Put your hand on your butt and go like this. You'll feel it squeeze, right? That's hip extension. So my glute is the prime mover during hip extension. When we're referring to this, I always like to use the Batman analogy. Batman is the main hero of the story, right? He's the main character, right? So he is the agonist of the story. It's the main person we're talking about. Now, you always have synergist muscles as well. Synergists are muscles that assist prime movers, right? And so the hamstrings are a synergist during hip extension, right? And so my hamstring, which is down here, it actually does hip extension as well, but it's not supposed to do the main job. My glute is doing most of hip extension. My hamstring is assisting in it, making it better, right? So your hamstrings are a synergist here. They're the Robin of the story, right? They're the sidekick. Your hamstrings are synergistic with your gluteus maximus during hip extension. So your prime mover is Batman. He's the one doing most of hip extension. Robin is the synergist assisting during hip extension. Now, earlier I mentioned muscles can only pull, right? So if I ever need to get my leg back from this position into this position, which is the exact opposite, I need to have a muscle that pulls in exactly the opposite direction. So every muscle in your body has an opposite muscle on the other side of the joint that does exactly the opposite thing. And that is called an antagonist, right? An opposite of an agonist. And it's muscles that work in the opposite direction. So they work opposite of your prime movers. Your hip flexor complex is the antagonist. If you think of Batman being the main character, his main arch nemesis is the Joker, right? He is the exact opposite of Batman. So my glutes go this way, my hip flexors go this way, right? And then you've got all these muscles that need to hold everything in place while all of this is happening, and those are called your stabilizers. So stabilizers are muscles that support to stabilize the body while your agonists and synergists are performing their movements, right? So your abdominal complex keeps your spine in place while you're doing hip extension. I always like to think of this as like Alfred the butler. He's there to provide emotional support and tea to Batman and Robin, like after they're done fighting crime. So there's like our little analogy there, right? Now, here's the thing. I was talking about hip extension. So because I was describing hip extension, the glute was the agonist, the hamstrings were a synergist. Now, if I were talking about hip flexion, and that's the main thing I'm talking about, now suddenly my agonist, the main mover, is the hip flexor, and the antagonist is now the glutes. So it depends on what movement you're talking about. That's what determines whether it's an agonist or an antagonist. We are going to be using this language a lot when we get to the second half of class. So if I'm describing, I'm going to really turn this down. If I am describing ankle plantar flexion, right? That is this movement right here, right? The prime mover for ankle plantar flexion is my gastrocnemius. That is the agonist, right? And the antagonist is on the opposite side of the bone. That is my anterior tibialis, right? So this is the agonist for plantar flexion is the anterior tibialis. The antagonist for plantar flexion is my, wait, what did I say? Oh my God. Take that back. I'm pretty sure I said the wrong muscle. The agonist for plantar flexion is my gastrocnemius. My antagonist for plantar flexion is the anterior tibialis. But if I go here into dorsiflexion, my agonist is the anterior tibialis, and my antagonist is that gastrocnemius. So all of our muscles are arranged to go in the opposite direction. You have to pay attention when we're talking about what muscle does what. You have to pay attention to what direction you're going, right? My bicep could be an agonist one moment, and it could be an antagonist the next moment. It depends on what movement you're talking about. If I describe elbow flexion, this is the antagonist. If I describe elbow extension, it's the antagonist. What did I say? God, my brain's all turned around. When I say elbow flexion, agonist. When I say elbow extension, antagonist. Good Lord.
So Brad, with that example you just gave, so when you do a bicep curl, the eccentric always goes with agonist.
Antagonist.
Okay, yeah.
Yeah, love it. Yeah. So that's another thing. We're not into that yet. We're gonna get into that tomorrow, actually. But yes, your contractions, you've got concentric and eccentric, right? Concentric is, this is actually another way you can tie that together. Whenever a muscle is doing concentrically, it's the agonist. Whenever it's pulling, it's Batman.
Oh.
Whenever it's relaxing, it's the Joker.
And they're always like in pairs.
Yep, and they're
like
always in pairs. Every muscle's got an opposite muscle. Yep. So whenever it's being concentric, it's Batman. And whenever it's relaxing, right? If it's relaxing, that means it's going in the opposite direction of when it pulls. So that means that it's being the Joker in that moment. It's being an antagonist, right? When my bicep contracts, my tricep relaxes. When my tricep contracts, my bicep relaxes. So yeah, that is arranged that way. And then at the end here, we just have some examples, right? So your agonist, and we put like a chest, a back, and a leg exercise here. So during a chest press, your agonist is the pec. And then during a chest press, your synergist is like your anterior deltoid and your triceps. And then like your stabilizers are like the rotator cuff. And then your antagonist would be opposite of your pec. You just go straight to the other side. That's your posterior delt. And there's some more examples in there as well. But that is that we are going to spend tomorrow looking at those types of contractions. We're going to look at concentric and eccentric, and we're going to look at starting to get into some of our terminology that we're going to use. Tomorrow is going to make a really good like flashcard day.
So I got a question. How you balance out? How do you know you balance out the tricep and the bicep?
Good question. It depends. Is your joint sitting neutral, or is it sitting where you like walk around like this all day? You know, because if it's bent like that all day, that means that you probably, like, if it's not sitting straight and it's sitting kind of in this bent motion here, you'll sometimes see people like stand in like this or like this, right? That bent means that one side is pulling a little bit and it never stops, and the other side is being inhibited. The other thing you can do is you can put stress on the body by moving them through like a certain range of motion. And if they compensate during that range of motion, it'll tell you, and you'll go, you got overactive, you know, so-and-sos, right? So if I like go like this, right? Let's say I'm supposed to squat, right? But rather than squatting like that, I'm gonna squat like this, right? I'm gonna do my squat here. And I do this like, see how my chest is super low, right? That's not what we look for in a squat. That's not good form, right? So what happened is I had to tilt my chest forward because I wasn't relaxing my calf muscles. My calves refused to relax. And so because they refused to relax, they kept my leg in this position. When it was supposed to go into this position, but I kept it here. Seems like a really small difference, but what it does is that means that as I squat, I have to lean forward. And so when I lean forward like that, I know that this muscle didn't relax. It didn't relax because my calf muscles were too tight.
That's how you get them cramps and stuff, huh?
Yeah, but that's also how we as trainers, we basically try to put you through a specific movement that puts a certain stretch on certain body parts. And if you don't move the way you're supposed to move, I know you have overactive muscles.
Yeah.
So that's what we're going to learn in this class, but I mean, a little bit in this class, but next module, when we get to PFT 101, that's going to be our main focus. We look at like which assessments put stress on the body in certain ways. And then we use that to analyze which muscles are overactive and underactive. So I'll show you one example of that here. So if you do like a push-pull assessment, see how this girl is hiking her shoulders here? I know that if she's hiking her shoulders like that during a pull, these muscles are overactive. She's supposed to be using these muscles back here, but instead she's doing this, right? That's an overactivity. So that's how we spot it. We put you through a certain type of stress. All right, guys, that's today. I'd say today is the hardest, this is the toughest lesson in the first half of class. The next two aren't so bad. There's a lot of terminology in the next two, but it's nothing that can't be solved with, you know, reviewing your notes. This one's really just the most technical day.
Yeah, that last picture you showed, it looked like she was squeezing instead of pulling, you know what I'm saying?
Yeah, totally. And that's what you do. That's what people do, you know. They'll lean or they'll tilt or they'll reach. You know, we look for these compensations. I love that quote from that video we showed you the other day where it was like, every movement is a test and every test is a movement, you know? And it's an opportunity for us to assess our clients. And, you know, you see a client who's like leaning into one side, you know, they got overactive muscles on that side. So you got to like strengthen them back to neutral. All right, so I'm gonna let you guys out of here. I will see all of you all tomorrow.